That was a really nice introduction. Thank you. I feel like I should just go home now. Actually, in a funny twist, when I started work at University of Washington, my first name is actually Rhiannon, and my boss at University of Washington had seen my application that said Rhiannon Jones, and then I showed up and I'm like, hi, I'm Lynne Jones, and they're like, wait, did we hire the right person? So I hope they feel like they hired the right person. Yes, I would like to thank you all for coming out tonight and to talk to you about finding icy worlds beyond Neptune, never before seen comets, and a little bit about killer asteroids. We already talked a little bit about a lot of these things. So with the lights here, they're shining on the screen a little bit, and it may be a little bit hard to see. But hopefully you can still see enough. Let me know if there's, yeah, okay, Bob says it's okay. So over the last sort of 100 years or so, there's been an ongoing evolution in astronomy. Astronomers used to go to the telescope and look through the telescope with their eye. So over here on the left we have Edwin Hubble at Mount Wilson. This is as recent as 1937, looking through the telescope by eye, and he made a very famous series of observations that showed that the universe was expanding, or is expanding. And the thing is that he was looking through the telescope by eye. This is what we tend to think of, as how astronomers functioned for so many years, from the time of Galileo down to within the last century. Over the last sort of century, looking by eye got replaced by using photographic plates. The advantage of using photographic plates is that you can see things which are fainter because you can leave the photographic plate at the end of the telescope and you can expose for longer. So it's essentially like using a longer exposure time with your digital SLR camera. The other thing is you get a permanent record of what you saw. So you can take an image today and compare it to one you took 3 years ago, and you can look for differences that you might not have noticed or thought to write down 3 years ago. Now, since that time, the CCDs, charge coupled devices, but we all just call them CCDs, have been invented. The advantage of CCDs, which are basically the same thing that's in your digital cameras, are that over time they've become even more sensitive than photographic plates, and you have much bigger fields of view. And the best thing about it is that the data is in a digital format, so you can put it right into the computer. You can add images together. You can run algorithms and software over the images so that you get a record of what you saw, and you don't have to necessarily measure everything by hand. So this is an ongoing evolution in astronomy from very laborious and looking by eye, writing down what you see, to using photographic plates, which are still pretty labor intensive, to using the CCDs and getting this digital data. Now, as we've become even better with writing software to understand what the CCDs are telling us, and as the CCDs have gotten bigger, we've started to move into the era of surveys. So over here we have, up at the top here on the right, we have a student at the telescope with a CCD, so you can see all of the computer banks that she's looking at, and over here would be the computers for operating the telescope along with the telescope operator. So we go from quite a different sort of setup, but now we're starting to use surveys where you have all these images, but the individual astronomers are not necessarily looking at all of the individual images that we've run software over, and so now we have sort of a big list of what we saw in the images, and you might actually just go and look at the list. So we've kind of gone, it's a very different sort of environment. Instead of going to the telescope and having a few next to the telescope, you do that sometimes, but you also work with these big databases, basically lists of all the objects. I was going to say maybe we'd take questions at the end, but I think maybe you had a question? Yeah? Okay. I have a toddler myself, so I feel like I must answer this question.
How hot is the sun?
Oh, how hot is the sun? Okay, the sun, the center is very, very hot. At the outside, it's sort of around 6,000 degrees. Okay. Very hot. Okay, so we've kind of gone from gone now into the era of what we call big data in astronomy. Things are quite different. You get really big data sets. And at the same time, we've been able to learn a lot more about the minor planets in our solar system. So when I say minor planets, I mean things like asteroids and comets. And so there's some pictures of these over here. This is one of the very big asteroids, and I think it's probably pretty hard to see now, but this would be one of the darker asteroids, probably comet right here, the core of a comet. So these are minor planets. This is what I mean by a minor planet. They're basically rocky or icy, small things in the solar system. Some of them are round, but a lot of them are not. As Mario said, they vary in size from very, very small. We don't really have a lower size of it, up to sort of the size of our moon or a bit bigger. And over the last sort of 20, 30 years, because of that advance in going from looking by eye to using photographic plate, and now in the last 30 years using these very large surveys and large format CCDs, the number of minor planets that we know about has increased very dramatically. So over here, this might be a little hard to see, but this is sort of about 30 years ago, and the number has increased by many hundreds of times. So today, we know of about almost 1 million objects in our solar system, and most of them are main belt asteroids. So these are mostly things which are orbiting between Mars and Jupiter. Most of them are far away. Over here, we have sort of a top-down view of our solar system. And in the center here, so this is the overall solar system. Hopefully you can see a few white dots, at least in the outer parts of the plot here. And so this circle here indicates the orbit of Neptune. And you can see we know of a few things further than Neptune. And these are the things we call Trans-Neptunian Objects. Sometimes you call them Kuiper Belt objects. And there are some comets here too. Then you see very close down in the center here, you can see sort of a denser spot showing that looks yellow. If you look up to the top, that's sort of a zoom in of that area. And here you can see very clearly the main asteroid belt. So these are things, the inner part here would be about the orbit of Mars, the outer region is about the orbit of Jupiter. So the orbit between Mars and Jupiter, and the reason we know about so many more main belt asteroids than the objects very far out in the solar system is because the things out in the outer edges of the solar system are very far away. That means they're very faint. So it's just harder to see the things out here than close in the main belt. So, as Maria said, I'm going to talk about all of these minor planets and why they're interesting. We'll click over to here. So up here is the asteroids discovered by the Sloan Digital Sky Survey. So this was a very big survey. Remember I said we were entering the era of large surveys. The Sloan Digital Sky Survey was one of these very large surveys. And they found a large number of asteroids, almost 100,000. What's interesting about those asteroids is that they also were able to measure things like the color of the asteroid. I'll talk a little bit more about that in a second, but yeah. And then down here, and the movies will loop. These are all of the currently known Trans-Neptunian objects. So and here they're color coded. They're coded by their size. So the bigger objects are actually bigger things. Up here, they're just coded by the color. So, this is going to run a little bit, and I'm going to talk a little bit about why minor planets are interesting. So they're interesting for a couple of reasons. So, first of all, there's a lot of them. So, if you think about flipping a coin, for example, if you flip a coin twice and you got two heads, you would think, okay, that's a little bit unusual, but it's not really unusual. If you flipped a coin 100 times and they all came out heads, you would think that's very unusual. That's statistically significant. So what's nice about the minor planets is that there are so many of them. So if we see things in the minor planets, like how they're distributed in space, what their size distribution is, so how many big things versus small things, what their colors are. So for objects in the solar system, colors roughly translate to what they're made of. Things which are stony tend to be blue. They look blue to us. And things which are very, very dirty or organic, have organics on the surface, tend to look red. It's just a property of how they reflect light. And so when we look and we can measure their color, then we can say, okay, these are roughly made of this kind of thing, these are roughly made of this other kind of thing. And so by being able to look at what the objects look like and what their composition might be and how they're distributed in space, because we have so many of them, that can start to tell you statistically about how planets form. So if you have a theory that predicts where the giant planets will be, for example, you only have 4 different constraints on the end result of your theory. So there can be a lot of different theories that produce those same 4 giant planets, but it can be much harder to produce those same 4 giant planets and the millions of asteroids and Trans-Neptunian objects. And in fact, these minor planets gave us the first clue that we didn't really know what was going on with planet formation in our solar system. So when we looked at, when we started to find solar systems around other stars, so exoplanets, we found, first of all, that they tended to be much larger than the planets in our solar system, and that they tended to be much closer to their suns. And so we said, oh, that's very weird. We don't understand that. And people started to think, okay, well, maybe these very large planets form further out in these other solar systems around other stars, and then they migrated towards the star. So that you would basically, you'd form your giant planet, and here's your star, and then it moves in slowly. And they thought of various mechanisms to understand how that could happen. But the basic idea was that the takeaway here is that planets don't necessarily stay in the same place. And then when we looked at the minor planets in our solar system, in particular, these objects in the outer parts of the solar system, the Trans-Neptunian objects, we saw that they were distributed in space in a kind of unusual way. And we said, that kind of seems to show that our planets have moved around over the history of the solar system. And so this is why the minor planets are very interesting for studying how our solar system evolved. They also, because they are much smaller, they're also a useful test for how you actually build up things from tiny pebbles into larger chunks like the minor planets, and then how those minor planets might actually join together to form larger planets that they live on, for example, terrestrial planets. And so they're a useful test of planet formation theories as well. So that's why we get very excited about knowing more about the minor planets and things all the way from near-Earth objects, main-belt objects, and Trans-Neptunian objects. And that's where LSST comes in here. So LSST, the Large Synoptic Survey Telescope. We have some LSST fans. So LSST, you'll hear much more about LSST over the next week, and this is the project that has brought us all to town. So LSST has 4 major science goals. The first of them being to explore dark energy and dark matter. And you'll hear much more about this on, Thursday, from Jim Bosch.
Dark matter is Wednesday.
Wednesday, okay, Wednesday. So if you want to learn about dark matter and dark energy, very interesting topic. There'll be a talk on Wednesday by Jim Bosch. This basically, if you want to boil this down to its simplest point, what this means for LSST is we have to go out and measure very precisely the shapes and positions and colors of about 10 billion galaxies. Then the next science driver that we have is to map the Milky Way and local volume. And you have a talk on Monday. Oh yes, by Beth Woolman, who's going to talk about mapping the Milky Way and local volume. This again comes down basically to saying we have to measure the colors and position and properties of about 10 billion stars. And then the other aspect, science driver for LSST, is to explore the transient and variable sky. Now, there's a lot in the sky that we've seen. You've all seen very pretty pictures of the sky from Hubble Space Telescope, for example. What those pictures don't show is what it would be like if you had a movie. We don't really have a deep movie of the sky, because we just haven't had the resources to go out and make that movie, essentially. So this is an important science driver for LSST, and it basically boils down to we want to look at the sky, everywhere in the sky, about 1,000 times over the lifetime of LSST. And then the science driver that we're hearing about tonight. Oh, sorry, and the transient and variable sky. Actually, there's a talk on Thursday. Yes, by Lucian Walkowitz. To talk about the transient variable sky. Now, so I'm talking about our other science driver, and I won't say fourth because these are all equally ranked. They're science drivers which were chosen so that the telescope could be a next generation survey that advances all of astronomy. By choosing these science drivers, we hope to pick up a wide range of useful data for pretty much anything you could think of for astronomy. So the last thing is inventory of the solar system. And this one basically boils down to discover 10 million minor planets and measure their properties and so on. Yeah, oh sorry, that's tonight. That's what I'm going to talk about. So what is the Large Synoptic Survey Telescope? And I'll talk a little bit about the project now. So LSST is an ongoing project. We are currently in our construction phase. Operations should start around 2022, and then they would last till 2032. So it's a 10-year survey. The telescope is being built down in Chile. Just here's Santiago, this is Chile. So the telescope is being built just outside of a place called La Serena. This is very close to some other telescopes which are already down in Chile. And actually, at the top here, you can even see this is the peak where LSST will be going, and you can might be a little bit hard to see, but these are other telescopes which are already there plus 12. And this is an artist's conception of our telescope, along with, we have some little auxiliary telescopes that help us with calibration. So this is not constructed yet. We actually laid the first stone already earlier this year, but it's still definitely under construction. Those science drivers tell us what the telescope should look like physically. In order to measure those 10 billion galaxies and 10 billion stars, and to be able to look at the sky, the entire the sky that we need as frequently as we should, we need a very big telescope. So it's a 8.4 meter primary mirror. Because we have things like that little hole in the center, then we end up actually on the effective diameter of the telescope is 6.7 meters. But this translates to sort of about 27 feet, if that's appropriate. Oh, and over here, we have a picture of our mirror. So our primary mirror actually exists and has been built. It's actually also been polished now. This is a picture from just before it was polished. That's why you have people sitting in the middle. I don't think we would do that now. And then this is a good part of the LSST team at the time.
May I ask, why geographically, why did they use Chile?
Oh, that's a really good question. We considered sites in Chile and in Mexico. We didn't think about going to Hawaii. Hawaii is actually very difficult to build on these days. They may have thought about it early in the process, but decided to consider just Chile and Mexico. The weather and infrastructure was slightly better in Chile. So when you pick a site for a telescope, you want to have dark skies. You want to have good weather so that you can look at the skies as often as you can. And you want to have things like good roads and stable, just nice infrastructure, lots of electricity.
The other telescopes you mentioned, those telescopes that run 60 minutes earlier this year or last year?
The other telescopes that were on the same ridge? I actually don't know which ones were on 60 minutes earlier this year, so, sorry? Oh, ALMA. ALMA is further north, actually. And ALMA is a lot higher. ALMA is actually kind of ridiculously high, but because of the kinds of observations that they wanted to do, they had to be ridiculously high.
So what's the altitude on this, or will be?
We're about 7,000 feet, right? Yeah. 2.6 kilometers. 9,000? 9,000 feet. Okay. ALMA is about 16,000. Yeah. Yeah, they did have to use oxygen while they were doing the construction. It was tough to build ALMA. Okay. The other thing that drives, because we want to look at so much of the sky so frequently, so we have the big mirror so we can look very faint in each image, but then we have a really big camera. And this is the thing that's actually really new about LSST. An 8.4 meter mirror is interesting. It's sort of among the biggest in the world now, but when you're talking about building 30-meter telescopes, sort of as your next generation telescope, this is not super huge. However, the camera, this is 9.6 square degrees that you would be looking at. That's about 3.5 degrees across. So if you hold sort of 3 and maybe a little bit of your next finger up at the end of your arm, that is about 3.5 degrees across. It may not seem that impressive, as that's how much sky that you see in one go. However, most telescopes today, you might have one finger, and if you were looking with Hubble, you might just have like sort of a fraction of that. I think Hubble is about a hair or pea or something like that across. It's very, very small. So, yeah. So in comparison, this is a really, really huge camera, and it's actually with the amount of resolution that we have with this camera, it's never been done before. There are 189 different CCDs across the field of view. So this is a simulation of our field of view. So you can see there's some dark spots because they don't fill in all the corners. There's other machinery basically to help us guide the telescope in the corners. And then these are all different CCDs across the whole field of view. And if you want to see what that would look like on the sky, this is a comparison. So this is 3.5 degrees across. The full moon is about 0.5 degree across by comparison. So this is, so you've got 7 moons across your field of view. This is really, really big. Okay, so those 189 CCDs actually translate to 3.2 gigapixels. So it's a lot of data, like Mario was saying, it's a lot of data even in just one image. And then if you remember, we're looking at each point in the sky about 1,000 times. So basically you're taking an image like this between 800 and 1,000 times a night on different parts of the sky, and then you keep doing that for 10 years. So you get a large amount of data at the end. Okay, so over here we have sort of what the outside of the camera looks like. It's a very big camera. Also, LSST is an optical telescope. So we're not, so basically we're looking at wavelengths that correspond roughly to what your eye can see. Now, astronomy CCDs are a little bit different than the cameras which are in your phone, for example, or your digital SLR. The cameras which are in your phone, in each pixel, they actually have 3 or more subpixels which are sensitive to different colors. So in each sort of pixel, you have something that is sensitive to red, green, and blue. For astronomy, the CCDs are actually much more like black and white. So if you think of them as a black and white camera, how do we ever measure colors? We do that by putting a filter in front of them. So it'd be like if I go over to this light and put a red filter in front of the light, then you're seeing only the red wavelengths. So we have a series of filters which we call U, G, R, I, Z, and Y, and we put them in front of the camera one at a time, and that lets us see that wavelength of light, or that range of wavelengths of light. And then we put a different filter in. We can measure the different wavelengths of light, and then you can look at the difference in intensities between the two to see if something is red or blue. So if something is red, and over here we actually have sort of this is wavelength. So this is very small. This would be blue end, and this is the red end. And these curves show the response of the LSST system to those wavelengths of light. And one of the interesting things here that I actually didn't realize until I made this plot is that the human eye is only sensitive to wavelengths between sort of about 400 to about 800 nanometers. And that corresponds to the area here which has actual colors. And the points which are just black are things that your eye couldn't see. So even though LSST is an optical telescope, we actually do measure wavelengths of light that your eye can't see. And here you can see we have U, G, R, I, Z, and Y. So if something is very red, it will put out a lot of light in red wavelengths, and when we put the red filter in, we'll see it look very bright. And then when we put a blue filter in, it would not look very bright because we're blocking most of the light. Conversely, if something was very blue, we would see a lot of light when we use the blue filter and not so much when we use the red filter. And so that's how we go and we measure the colors of stars or minor planets. So the next aspect of the telescope is to understand how we're going to use this telescope to look at the sky. So I said we had to come down and measure 10 billion galaxies and 10 billion stars, and then look 1,000 times and discover about 10 million minor planets in the solar system. So that translates to how we look at the sky. So here's a good example. This would be the whole sky, and this is sort of the main footprint for our survey, this yellow area. It's in the southern hemisphere because our telescope is in the southern hemisphere. So we can see things in the south very easily. It's hard to see things in the north because they're just, it's easy to look up, it's hard to look across at the sky for telescopes. So we cover this large amount of sky, and we take images over and over and over for 10 years. So how we do that is we go on the sky, we take 2 very short exposures, we wait about 30 minutes, we come back, we take another set of 2 exposures, then we wait a few days, then we come back at that point in the sky and we take another 2 exposures, and we wait a few minutes and we take another 2. And we do that over and over and over again as long as the field is visible throughout the year, over and over and over again for 10 years. Here we have a little movie we have simulations. I said I worked on simulations a lot of what LSST will do. We have simulations of how LSST might look at the sky. We call these our simulated surveys. we do this because we want to understand, first of all, can we actually look at that much sky with the realistic weather conditions, for example, and realistic times to move between fields. But then also, can we, if we look at the sky with that kind of pattern, can we actually discover moving objects, at least solar system objects? So this is the whole sky. Now the whole sky is not visible at once, so this circle here tells you sort of how much the telescope could possibly look at. And then, oh, that was a night. This is the next night. And you can see the telescope is just moving around in the sky. It's looking at fields with this cadence that we talked about, where you look at the fields and you come back within 30 minutes, and then you come back another several nights later. And it's kind of hypnotic, you know. It's like when I started making these movies, I would just sort of sit and stare at it for a while. It's almost a little bit like Centipede sometimes. So we're actually also going to use these movies to help us understand our simulation software. And one of the things we learned is that we actually need to do better at scheduling the telescope. So there's that. Okay, so now the biggest challenge in the telescope is, once we've built it with this big mirror, big field of view, big camera, and we've figured out how we want to look at the sky, what do we do with all of those images? So when the images come into the telescope down in Chile, they're actually transferred over the internet up to NCSA, which is in Illinois. So it goes from down here up here to Illinois, and it does that within 60 seconds. Actually, I think it's a shorter time, but say about 60 seconds. And once it's there, then we go through some manipulation of the images so we can identify all the things which are moving and changing. So this includes minor planets, because how we identify minor planets is we look for a dot. Basically, they look like dots, so they look like the stars, but they don't stay in one place. So as you know, when you look at planets, you see them moving across the sky slowly night after night. And the same thing is true with minor planets. So that's how we find them. I love the enthusiasm. So we go through and we identify all these things that have changed, and we do that every night. And then every year we go through and we do a very precise manipulation of the images. Basically, we're trying to turn all of these images into big lists, right? So we take our image, we go in and we measure all of the stars, and we turn them into really big lists that tell you where the object is, what it's shaped like, how bright it is, anything that we can think of that might be useful to astronomers trying to study the data. And so we put them in these big lists, and then we make the list available, and people go in and you search it using queries and things like that. The interesting thing about LSST is we have so much data, and also that we are paying a lot of attention to how we're trying to process that data to turn it into these catalogs. So we are trying to make very, very precise measurements of where things are. That's astrometry. We're trying to make very, very precise measurements of how bright things are. That's the photometry. And how precise we want to be with the astrometry and photometry are sort of at least a factor of 2 better than anybody has ever done before. And a factor of 2 doesn't sound so hard, but it turns out that this particular factor of 2 really is very hard. And so this is part of the reason why we come and we have our meetings every year to try and talk to each other and understand, okay, really, what are the errors on this thing that you're building, so that we can understand what effect that might have on things like astrometry and photometry. And then I said, we want to discover about 10 million moving objects. This is the minor planets throughout the solar system. This is actually an interesting comment. You can say detect, which might mean that you know that there was something there, but you didn't really, you just knew that there was something there that wasn't there later, right? Because I said the minor planets all moved. So if you saw something that was there and then it wasn't there, that actually doesn't tell you that it was a minor planet, and it doesn't tell you the interesting information about the minor planet. So in order to really say you discovered 10 million minor planets, moving objects, you actually have to do something more complicated. You have to take each of your detections. So, and actually, over here, let me just, here is an actual moving object. This one is moving very fast, so it looks elongated, but a lot of the time it would just look like a star, essentially, that moves slightly. So this would be one exposure, one time that LSST looked at the sky. And this could be an example of another time LSST looked at the sky. And you can see that the asteroid in this case moved. And then if you look at the difference between the two, so you basically, you take the two images and then you subtract the two. And then it might be a little bit hard to see in the glare of the lights, but there's a hole here, which is where the first object was. And then there's a bright object here, which is where the second object was. And all the stars, all the stationary things disappeared because you subtracted them and they were the same. So we do this step for all of our images. We make a difference image between the image you just took of the sky and what was sort of stationary there before. And that lets us see all of the things which changed. A lot of these might be moving objects, but it might also be some other things. And then we basically play connect the dots. So in one night, you might have a detection of something that moved or changed in one spot. And then later in that night, you might have a detection of another thing that moved or changed. And it's a little bit different location. And then on another night, let's say 2 nights later, you might have another few detections. And then on another night, you have another few. And so what makes this hard is that you actually have lots and lots of other dots that I didn't draw up here that are sort of competing with, can you draw a line through those other dots? So if you, for example, had some other things that were just up here, you might have tried to draw a line like this. But instead, if you get enough things that you could line up the dots, then you can start to say, this is the moving object, these things connect, and it's not this other potential combination. So you play this game, connect the dots, and we've been working very hard on figuring out exactly what the best way to do this is, because it gets to be actually very hard computationally. But hopefully at the end of it, what you come out with is an orbit for your minor planet. So the orbit describes how it moves on the sky. So this is actually an image from Wikipedia, which is lovely for getting images explaining complicated astronomical concepts. But the idea is, here's the orbit of a minor planet. It has some distance from the sun. It has some inclination that it is in the sky. And it has some sort of difference from roundness. So if it's very round, you say its eccentricity is 0. If it's very elongated, very much an sort of oval shape, its eccentricity might be closer to 1. And then there's some other parameters that describe how the orbit is oriented in space. We care about them all, but the sort of some of the primary ones are the semi-major axis, how far it is from the sun on average, the eccentricity, how elongated it is, and the inclination, which tells you how tipped it is relative to the rest of the object, the plane of the solar system. So we really, really want to know the orbits of everything. So why do we want to know? First of all, the orbit lets you, once you know an orbit for an object, you can predict where it will be in the future. So if you want to go out and know where that thing is and you want to make more measurements of the object, then you have to know the orbit. You also have to know the orbit if you're going to play the game of, I want to understand how the objects are distributed in space, and thus understand planet formation and evolution. The orbits are critical. You also, if you're interested in the killer asteroid problem, you really want to know about the orbit, because you want to know if it's going to come and hit the Earth. So the orbits are really important, and this is the hard part about saying that you discovered these large number of minor planets. So at the end of the day, what will LSST do for planetary astronomy? And this, I actually made this table for a different meeting, but I like it so much I had to show it here too. So this is basically telling you about why LSST is a leap forward for planetary astronomy and understanding our solar system. So these are in each column here. This is like the near Earth objects. So currently we know of about just over 10,000 near Earth objects. So these are the things which are very close to Earth, have a subset of them have some chance of potentially hitting Earth. With LSST, we will find about 100,000. So we know we will learn about 10,000 or 10 times more. And importantly, we will get lots of observations of these objects. We get about 60 observations sort of on average for the brighter ones. And we'll be able to watch them for 6 years. The reason it's not 10 years is because you don't get to watch the objects. At some point they go behind the sun, and so you can't get the full 10 years to look at them, just because of how they move and how the Earth moves, and so we just don't line up in the right way for a while. So the nice thing about getting lots of observations, and you can see there's lots of observations across all of these, is that it lets you do things like understand what the shape of the object is and how the object is spinning. And these are also things that help us learn about planet formation, because if everything is spinning in the same way, that's clearly a signal that there was something about planet formation that made all of the objects end up spinning in the same way, and so whatever your theory is, it better explain that. Okay, so that's the near-Earth objects. The main belt asteroids, similar sort of thing. We know about a lot more main belt asteroids today, just over 600,000. But with LSST, we expect that number to come up to about 5.5 million. It's plus or minus a bit depending on what the size distribution is. I actually figured out the other day if there are more smaller objects than I assumed when I calculated this number, we might actually have 14 million. So that would be great. And again, you can see these objects. You get about 200 observations for the bright ones over 8.5 years. You can see the main belt asteroids and all of these other things a little bit longer, like typically 8.5 years instead of 6 years, because again how they line up with the Earth's orbit, how they move relative to the Earth, means that they just stay visible for longer. The Jupiter Trojans. So these are a cloud. I didn't talk about these much, and I won't. But these are basically a cloud of asteroids that are. They move in the same orbit as Jupiter, but just slightly offset so that they don't ever run into Jupiter. And then the Trans-Neptunian Objects and scattered disk objects. So currently, this is the population we know the least about, but it's actually one of the most scientifically interesting because of the fact that they're very far away in the solar system. They're not quite as they haven't had as much push and pull to them as the main belt asteroids, which suffer a lot of interactions with Jupiter. But the Trans-Neptunian objects, they do get influenced by Neptune, but to a much lesser extent. And so when we look at the Trans-Neptunian objects, we get a much sort of clearer view into how the giant planets might have evolved. And so currently we only know of about just under 2,000. There's not very many at all. And with LSST, we should be able to bump that number up to about 40,000, it should be great. So this is amazing, right? Across all of these populations and other small body populations in the solar system, we'll have an increase of about 10 to 100 times more objects to study. And if you remember at the start, I said one of the things that's really interesting about minor planets is that you have so many of them. So suddenly being handed an order of magnitude more objects is really amazing. It doesn't add up to 10 million. Yeah, so the 10 million is, if you include a little bit of sort of uncertainty for the main belt asteroids. Yeah. Yeah, I mean, almost everything is a main belt asteroid in the survey. It's not necessarily true in the solar system itself, right? If we were closer to the Trans-Neptunian objects, we would be able to detect a lot more of them. But because they're so far away, and things get fainter, so stars get fainter as you move something away. It gets fainter by what we say r squared, right? So it's the same thing as if you step further away from a light, it gets fainter by r squared, the distance squared. But in the solar system, it's much worse because they are actually only shining by reflected light. So in that case, the light has to go out to the object and bounce back. And so it actually gets fainter by the distance to the core. So it's really hard to see things in the outer solar system.
What's the minimum expected size of the objects that you see? Some things would block your view that are already in Earth orbit versus Jupiter's orbit.
So there's very few things which are actually in Earth orbit. The minimum size that we could see, it depends a bit on how bright on what the object is made of. Again, so because some things are just shinier than others, since they're all reflecting light. If something has a very dark surface, that we call it a high albedo, or sorry, low albedo. If it's very dark, it absorbs a lot of light. Then it would be very hard. It would be harder for us to see. If it's very shiny, we can see things that are much smaller. This is actually one of the reasons why it's fairly easy to see Pluto, because it's quite shiny compared to a lot of the Kuiper Belt objects. But the minimum size, and then it depends on the distance to the object, very by a strong factor. In the main belt asteroids, sort of about the minimum size you can see is about 100 meters. And for the near-Earth objects, we can, again, then it depends very sensitively on how close they are to us and how close they come. But we could see, we could see down to sort of 40-meter objects for things that come close, and even smaller for things that come very close to sort of 40-meter limit. For things in the Kuiper Belt, the Trans-Neptunian objects, we can see things down to about sort of 400 meters, 200, 400 meters, 400 meters, let's say. But most of we start having some chance of not discovering them at that point, because at your faintest magnitude limit, you always have some chance of not seeing something. Whereas if it's very, very bright, you're always going to see it. So I always say the smallest things we can see are probably about 400 meters, kilometers in the outer solar system, and then it goes down to sort of 200 meters in the main belt asteroid. So this is I was going to say, so these Trans-Neptunian objects are the distant icy worlds beyond Neptune that I was talking about, and they are just very interesting because of their how they preserve the signatures of the evolution of the solar system. Anyway, so it's a little bit hard to see here, but this is the outer parts of the solar system, and there are little dots, white dots there, but they're a little bit washed out by the lights now. Then there's also these very loopy, sort of more eccentric orbits. So they're non-circular objects, and these are things which we've found when they're at their sort of closest approach to the sun, typically. And we found them, and they're very interesting. They give us a lot of information about what could have happened in the outer solar system and what you must be able to happen in order to sort of be able to explain the distribution of these objects and what their orbits look like. The first sign that we had that in our solar system planets were moving around and migrating over their history was actually discovered in the outer solar system. So when you look at the objects, when you look at their orbital distribution, the orbits of the objects, you can see that many more of them than we expected were moving in resonance with Neptune. And when I say they're moving in resonance, what that means is that for every 3 times Neptune went around the sun, the Trans-Neptunian objects, these are the ones that we saw more of, that we were interested in, move 2 times around the sun. And this is the same kind of orbit that Pluto has. Every 3 times Neptune goes around the sun, Pluto goes around twice. And we saw a lot more of these objects than we expected to find. If you just had them randomly distributed, you would see a lot more in sort of the just regular, I don't care about Neptune kind of orbits that some of them have. But we saw a lot of them moving in resonance with Neptune, and that was very odd. And so that led to the first theories that maybe Neptune had migrated. And at first we thought, well, okay, this was probably a very slow migration. But as people started studying more of these objects and studying objects throughout the rest of the solar system and sort of trying to tie the whole picture together, this theory called the Nice model evolved. So the Nice model is really interesting. This was put forward sort of about just over 10 years ago. And you can see here, this is very early in the history of the solar system, and everything is was arranged more compactly in this theory. So one of the mysteries of the Kuiper belt is that not only do we see more things in resonance with Neptune, but we also saw less of them overall than we kind of expected. We were like, wait a minute, there don't seem to be as many objects out here as we would expect in order to be able to form all the objects that we see there. So the Nice model suggests that all the giant planets started on much more compact orbit, and then they migrated very slowly outwards. So this is in the early part of the solar system, and you can see the million years since the start of the solar system ticking along here at the top. And so everything, these are the orbits of the giant planets. There's Jupiter, Saturn, Neptune, and Uranus. And they're sitting there in this more compact configuration. And that helps with a couple of other theories on planet formation as well, like how do you build these giant planets so quickly? And then you see that it sits there, and then suddenly everything goes crazy. It's really hard to follow in those few slides because it happens very fast. But the idea is that they migrate. Jupiter and Saturn migrate slowly outward, and they migrate at slightly different rates. And then at some point in the history of this migration, Saturn hits resonance with Jupiter. So this is the same idea as when we were looking at the Trans-Neptunian objects, and we were seeing Trans-Neptunian objects which went around the sun 2 times for every 3 times that Neptune did. So that means they line up every 6, I guess, times. But in this case, it was a much stronger resonance. So what happened is, as they migrated slowly outwards, suddenly Saturn hit the 2-to-1 resonance with Jupiter. So that means every 1 time Jupiter went around, every 2 times Jupiter went around, Saturn went around once. And so they're lining up much more frequently, and that gives big kicks to Saturn's orbit. And so Saturn kicked out suddenly in the solar system, moved all these minor planets around, kicked Neptune and Uranus out further in the solar system too. So there was a lot of scattering from one planet to another. And basically you rearrange the entire outer solar system, and the idea is that this can give you the same orbital distribution that you see in the Trans-Neptunian objects today, more or less. We still have details to iron out here, of course. And it can give you that because you also notice that the density of those green dots, those would be the minor planets that are left that you started with. So the density of the green dots has dropped dramatically. So you have a lot fewer objects that are left. So you get that missing mass in the Kuiper belt. The other nice thing that this ties into is if you have this happen sort of somewhere between 500 and 800 million years after the solar system starts. Now, so the solar system overall we think is about 4.5 billion years old. So this is early in the history of the solar system, but not super early. So 500 to 800 million years after the solar system forms, and then you have this really big rearrangement of the outer planets. You scatter the minor planets everywhere throughout the solar system. And when we look at the moon, in about this time frame, we see a really heavy spike in the cratering record. So when you look at the craters on the moon, you you can estimate their ages, and if you look at how many craters there are, there's a really big spike at about the time this might have happened. So it's really nice, you know, you can start tying the NIES model into things you see throughout the rest of the solar system. So this is definitely something where the theory has been around for about 10 years now. People have really been looking at it pretty hard. There's still some people who don't really believe it. There's other people who are just like, well, let's, you know, iron out some more details. I think it answers a lot of really interesting questions and provides a nice theory to tie lots of things together. There are still things that we see that don't exactly match the NIES model. So there's things we need to sort out with this model. Like, so for example, one of the questions is, did we actually have a fifth giant planet that was also there and was just ejected from the entire solar system? We think that happens a lot with exoplanets, actually, so it wouldn't be that unusual. The other thing is that, so this is, remember I said we can look at the colors of objects, and that sort of stands in for what they're made of, their composition. And so for the main belt, when you look at their distribution with distance from the sun, you can see that this tells you how many objects of a particular kind are present at a distance from the sun. So as you move outwards here, we're going further from the sun. And as you go up here, it means that type of asteroid is more common. So asteroid types they have shortcuts with letters. But basically the interesting things here are the S, so those are stony asteroids, and the C, those are carbonaceous asteroids. They're more organics and red. They also tend to be darker. And you can see that they're distributed in different places, right? There's more S objects closer to the sun, and there's fewer further away, and then there's a big peak in the C asteroids further away from the sun. So this very steep difference across the distance of the main belt asteroid makes you think, okay, well, if they're distributed like this, then either something had to sort of sort them after they were formed, maybe, or you had to put things into those kind of orbits, or you had to just have a different composition that objects were made of. So maybe all the materials that all the objects were created from when they were building up from little pebbles, maybe there just was more carbon in the outer parts of the belt than in the inner parts of the belt, and there was more stony things in the inner parts of the belt. And that's actually what we thought for a very long time, but it was a little puzzling that change was so quick. And so now what we actually think is that maybe that wasn't the case, because it is really, really quick across the main belt asteroid. When we go out and we actually, so this is sort of a summary, but when you go out and you look at the asteroids from the SDSS, which I said was one of the very big previous surveys, you can see the same sort of thing. So this is distance from the sun. This is actually just telling you something about the tilt of the asteroids. But what's interesting here is that you can see close in, there's more of these green and red colored objects, and they're colored according to their observed colors, which, like I said, translates to their composition. And then in the outer parts of the belt, you can see that there's more of these purple and pink objects, or blue and pink objects. So it's just showing you, this is what we could do with a previous survey that had sort of on the order of 100,000 objects. With LSST, we would be able to make the same kind of plot, but have 5 million objects. So we can get a lot better detail, like we could look in here near these resonances, we could look at the gradient, we can do a lot more, we can have a lot more information. So that brings me back to the question, was it actually a composition gradient, or was it something else? Well, so this is actually another new theory for the evolution of the solar system. Maybe the composition was actually the same across the asteroid belt. We have no reason, we can't think of anything that would make it change dramatically across the main asteroid belt. But instead, what if Jupiter moved very early in the history of the solar system? So this model is called the Grand Tack model, because Jupiter comes in towards the sun, it migrates inward, and then it sort of tacks and goes back out. I guess the wall should almost have some sailing background. But over here, what you see is, so these are the orbits of the giant planets again. Things start out, again, more compact. Jupiter migrates inwards. Oh, and then Saturn came in and must have given it the kick to go back out. And then the asteroid belt is left a little depleted. But over here, what you can see is this is sort of some snapshots essentially, but instead of showing you it's a little hard to see here, but the red things are the things that started far in, and the blue things are the things that started far out. And you can see that they're sort of mixed together, but mixed so that the inner part of the asteroid belt afterwards is red and the outer part is blue. So that recreates that gradient across the main asteroid belt. But you can see over here sort of a graphic that shows you this maybe a little bit more clearly. So this would be at the start, the starting setup. So Jupiter, Saturn, and you have these C-type objects which are much further away from the sun. So it's easier to explain why that material is different because it's much further away from the sun. So we have a lot further. It's easier to explain that gradient because you have a lot wider area to be able to explain it in. And then the S-type asteroids, which are close. And so Jupiter migrates inwards. It scatters the S-type stony asteroids from the inside out, and then it moves back outwards. And when it moves back outwards, it scatters the blue carbonaceous objects back in, and so you end up with an asteroid belt that goes from stony, carbonaceous, and then a little bit mixture in between in a short spatial scale. So migration can be driven by gas, a gas disk. It can be driven by planet-planet scattering, like in the Nice model, or it can be driven by planetesimal scattering off little planets. In this one, it starts out with the idea that because this is much earlier in the solar system, 5 million years, the migration is started from gas migration. It's driven by gas. And then I think that the turnaround is actually about the point when the disk sort of dissipates. And it's just back. So I should hurry because I think it is pretty late. So discovering new comets. This is a little bit. We will discover new comets as they come into the solar system and before they become active, and that will be a really interesting area of science for LSST. But the other thing we will be able to do is look at things which we didn't necessarily know were active before. So when we in the last sort of 10 years, we've discovered a handful, only about 12 objects in the main asteroid belt, which actually, we thought they were asteroids. We thought for a long time they were asteroids, and then suddenly we realized that no, they actually had little tails. And so that is an indication that there's something going on the surface. The most obvious explanation is that they actually have some water underneath the surface, and either just because maybe perhaps we didn't notice before, after all we knew about these things, we just hadn't seen the activity. We don't look that frequently at most things in the sky. This is one of the things LSST will fix. So it could be that, or it could be that there was a collision. The collision scraped the surface and unearthed some water, and then this water, on an asteroid, water behaves as what we call volatile, so it just outgasses. This is the same reason that comets have tails. So this brings us to the question, do main belt asteroids actually have water? We had always thought that they were just very rocky and that they did not have much water, certainly not enough to cause outgassing like this. So this is a really interesting area for LSST to explore. Currently, like I said, we only know of about 12 objects which show these signs of outgassing. With LSST, and they're all very small objects too. So with LSST, we are very sensitive to small objects, and we look at them a lot of the time. So if you just took our rule of thumb that we will know about 10 times to 100 times more objects, you might say we might discover 120 active asteroids, which is what these are called. But because we actually look at the objects much more frequently, we may discover many, many more. I wouldn't be all that surprised if we would sort of discover about 1,000 or more than 1,000 of these objects, which will be really interesting to study. So one of the things we don't know now is what exactly is causing those tails. Is it collisions exposing subsurface water? One theory I actually heard very recently is that it's actually just that the objects are rubble piles, and so when they have a collision with something else, they get shaken up, and they're just sending dust off the surface. So it'll be really interesting to see what happens with these sort of never-before-seen comets that are a different kind of comet. And, okay, our last thing, which it always gets people very interested. So killer asteroids. LSST will do a really great job about looking at the sky over and over again, detecting moving objects, and that includes things which are very close to the Earth. However, will we find one of these? Probably not. And probably that's not going to happen. So first of all, this is an artist's conception. So somebody drew this picture. It's very dramatic. However, the size of this object is really, really, really large. Even the thing that caused the extinction of the dinosaurs was only 5 to 15 kilometers across, which would be almost invisible on this scale. So if there was something out there this big that had the capability to hit the Earth, we would already know about that, even without LSST. And in fact, even without LSST, we've done a very good job of finding all of the near-Earth asteroids which are larger than 1 kilometer in size. 1 kilometer is sort of the order of an extinction level event. However, there are lots and lots of smaller things. And if you're here for the questions at the start, I talked a little bit about how you might get tsunamis or airbursts from much smaller objects. And this is an example of a very small object. This is the Chelyabinsk meteorite. And there's some really amazing dashcam cameras in Russia that captured this meteorite coming in. This was actually only about 20 meters across, and it came out of the direction of the sun. So actually really, really hard to find and detect before it impacted. It did injure about 1,000 people. It came in and it actually blew up in the air, and then fragments of it did land in a lake. This is actually a lake where they managed to retrieve about a sort of a meter-sized chunk of the object. But those people who were injured were actually mostly injured by falling glass and sort of other debris from as the meteorite streaked across the sky, it created a sonic boom, and then that boom blew out windows, and so the buildings were damaged, and people were then hurt by the buildings suffering their damage. So LSST will be able to see things like this if they are approaching from the right angle. Like I said, it's very hard to see things which are coming with a telescope on the ground. It's very hard to see things which are coming in from the direction of the sun. It's actually very hard to do that anyhow, just because you have the sun. You just can't point a telescope that way. So they're very hard to discover, but one of the nice things about LSST is because we have such a big mirror, we will actually be able to discover things like this earlier in their orbits. We will mostly be able to discover things which are larger than 20 meters. But we would be able to find some of these. Now, what is the next sort of hazard level threat for near-Earth objects? Congress actually has a mandate. So many years ago, they said to NASA, go out and find all of the very large objects. These are the 1 kilometer objects, and that was called the Space Guard goal. And that has actually now been met. So they found 90% of the objects which were larger than 1 kilometer in diameter. The next goal, so to reduce to the next level of risk that they deemed was a good, sort of the next level to go to, was to define 90% of the objects 140 meters in diameter. So 140 meters, again, it depends what the object is made of, how fast it's coming in, what angle it's coming in at. But this would be sort of on the size to cause significant damage to a city or small region. Again, depending on where it lands and how it's coming in and what it's made of. So to get to 90% completeness for 140 meters in diameter, you actually do need these next generation surveys like LSST. Just because the telescopes that we have now are just not big enough to get to that level. So with its sort of normal observing cadence, LSST will actually find about 75% of these based on our current simulations. If we change LSST's characteristics a little bit, we could meet that 90%, but probably the best chance of meeting that 90%